a few more examples involving direct proof of integers. We're going to say that for all x in z even, that if you take the fourth power of that number is also an even number. Right? And just to kind of verify that, we know 2 to the fourth, which is an even number, is 16. We know that 4 to the fourth is equal to 256, which is even. But we know 3 to the fourth is equal to 81, which is clearly not even anyway. All right, so it looks like that anytime we take the fourth power of an even number, it seems like it's going to work out to be an even value. Of course, the problem is if we try this for all the numbers, that we're going to be sitting here forever, literally. So we can't use exhaustion in this. So here's the process we're going to start with. Okay. Step one, remember, is to define your variables. So let's let x be an element of z even, right? And you don't have to write this, but you can say such that x is arbitrary but particular. And then, of course, we need the very definition of even. So we can say, by definition of even, we can say x is equal to 2k, where k is some element of the integers. So generally what I suggest to people is with the direct proof, always look at the left-hand side or the antecedent. So if x is even, then x to the fourth is even. So look at the antecedent to be able to define all your variables. Now you're going to look at the predicate or the conclusion, and you're going to say, okay, well, what am I going to do at this point to be able to verify that x to the fourth is even? So here's how we're going to do that. We're going to use substitution. Okay, so we're going to say by substitution, x to the fourth is going to be equal to 2k to the fourth power. Okay? And now we just have to do some algebra on this. Right? Now, we know that if we take the fourth power of 2k, that becomes 16k to the fourth. All right, and there's two ways you can write this, okay? If you've been teaching algebra for 20 years of your life, you know that that's something called the product of a power rule, okay? You can just say exponent rules if you don't know the specific rule, all right? So now if you do know that's product of the power rule, that's great for you. If not, just say exponent rules and that'll work nicely. What are we looking for? We're looking for z to be even, and even is of the form 2 times an integer. So we need a factor of 2. And so what we can do is we can rewrite this as 2 times 8k to the fourth, okay? And that's just clearly computation, okay? Or just making sure that you can factor it. And the last thing we're going to do is we're going to use integer closure. We know that 8k to the fourth, it's all multiplication. An exponent is just repeated multiplication. 8 times repeated multiplication is still multiplication. So we can say that this is going to be equal to 2. Let's just say p, okay, where p is an element of the integers, okay? And if you wanted to, you can say where p is equal to 8k to the fourth. And of course, we justify that by integer closure. Right? So every time we do something, every operation, we have to justify it. All right, so we're done with this because now what we noticed is we have x to the fourth is even and 2p is even. So now we can conclude. Right? Our last statement is we can say, thus, x to the fourth is equal to 2p. There's that transitive property, okay, because we just keep having equal. So x to the fourth is equal to 2p by above, and hence x to the fourth is even by definition of even. All right. And so we can conclude So we can say, hence, for all x in z even, we can say x to the fourth is an element of z even. All right, so pretty cool. That's what we're going to have to do to be able to verify these sorts of universal statements where we don't have a finite domain by using direct proof. Right? A third example. For all n in z even, minus 1 to the n is equal to 1. Right? And we know this. Right? We know that anytime we have minus 1 to an even power, it just becomes 1 because we're multiplying by an even number of times. So that's the strategy we're going to take. Remember, first part, define the left-hand side of your conditional statement. Okay, so, and by the way, going back to this previous, remember the numbering is just first is going to be variables, second is going to be the algebra, and then the third step, remember, is your closing or your basically conclusion. All right, so keep those three steps in mind. All right, so variables, algebra, conclusion. All right, so anyhow, going back to this, we're going to start by defining n to be an even integer. Okay, so we're going to say, let n be an element of z even. Okay, and we're going to say, of course, such that, and I'm going to put this in orange just because it's not necessary, but at least in my class, so such that x is arbitrary but particular. All right, we can just assume that. All right, we're not working with multi-dimensional sorts of even vector spaces or anything like that. By definition of even, we know that n is going to be equal to 2k, where k is an element of the integers. All right, so we could literally, if we wanted to, just take the entire first part right here and just copy it back down. Okay, so anytime we have a single even variable, this is how we can go through and try to define it. Now we're going to go through and do the algebra. And this is where we have to verify by substitution minus 1 to the n is equal to 1. Okay, so by substitution, we can say minus 1 to the n is equal to minus 1 to the 2k. Right? Now we're going to do some algebra. This is the same thing as saying that this is going to be minus 1 squared to the kth power. Right? I don't think anybody doubts that. Again, if you don't believe that that's going to be the power of exponent rule, then you could just verify it with a couple numbers, but this is the trick that you're going to have to use for this one. Okay, so this is just our exponent rule. Right, this one's not product of the power, by the way. This one's actually just the general power rule of exponents. And now what we can do is we can do some computation because we know that minus 1 squared is just 1 to the k. So this is by computation. And then finally, we have 1 to the k power. Well, 1 times 1 times 1 times 1 is going to be equal to 1, right? And how does that, what justifies that? Well, remember, 1 is the multiplicative identity, right? So if you really wanted to justify it, you would just say that this is the multiplicative identity. But you could just say exponent rules. All right. As long as you give me a justification, that's fine. All right. And what have we done? We've shown that minus 1 to the n, where n is an even integer, is going to be equal to 1. Okay, so third part, we can say hence, pi above, minus 1 to the n is equal to 1. All right, and we don't really have a definition. It just is what it is. And we can say, therefore, for all n in z even, minus 1 to the n is equal to 1. All right. This could also be true if we change this to odd, then it would be negative 1. All right. So, and that could be a further sort of homework problem or something like that, where you could utilize a lot of the same steps here. All right. So, in the next video, we're going to go through one or two more of these just to make sure you have this down, and then we can move on to rational numbers.